seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello and welcome to the Space Nuts podcast, episode 136. And if it's your first time finding us, well, a special welcome to you too. As many people have been telling us lately, they've recently discovered our podcast and are listening to the back catalogue from the very beginning. So that's lovely to know. And our numbers continue to climb in terms of downloads, and we really do appreciate that. So thank you, and don't forget to tell your friends. And joining me, of course, is my partner in crime, Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. It's great to be back in crime with you,
yes,
as we seem to be every week.
Yes, this is just a front. It's got nothing to do with anything else.
This is front, back and sides. This in itself is a big enough crime.
Now, I've had a very adventurous week since last speaking to you. I managed to catch the flu for the fourth time in 14 months. One was self-inflicted because I got a flu injection and then I got the flu.
Yes.
So I'm having a ripe old time, but I'm on the mend again. Hopefully this will be the last time I get it for the rest of my life. But on top of that, I am looking at the current temperature in my locality, which is in the central west provincial city of Dubbo, New South Wales, Australia, and it is 44.2 degrees.
Hang on.
That's centigrade. Yeah, I'm going to just work it out myself now. 44.2 equals Fahrenheit. Because, you know, those people up north and all. And see what the answer comes in at. 111.56 degrees Fahrenheit. It is here right now. And I'm feeling every inch of it. It is woeful. Anyway, we're going to get through it and hope that the air conditioner doesn't bust a gut. And what we're doing today, Fred, is we're dedicating the whole episode to listener questions. And just to précis the questions, so I don't read them all out at once, why is Uranus upside down, dark matter lensing, and cosmic microwave background after the Big Bang? They're the general nuts and bolts of what people want to talk about today. So, Fred, our first question comes from a young fella named Zach McEwen. He might be 85, I don't know. Love the podcast. It's perfect for listening to on my long night drives in the desert around Moomba, where I work. And we get great dark skies out there. He's talking about central parts of Australia, basically, central southern parts, I think. And one question, why is the axis tilt of Uranus so different to the rest of the solar system? Cheers, keep up the good work. Thank you, Zach. Zach, you really need to read Fred's book. Why is Uranus upside down? It was when I saw the question come in, I thought, this is absolutely perfect for Fred. And I think we've sort of been over this ground once or twice before, but it never hurts to go back again so Fred can promote his book, so Fred can explain the situation.
Well, actually, there's new work on it, Andrew. So it's a good question from Zach, and it's well determined. So the book, I have to say, Why is Uranus Upside Down? Yes, published, I think, in 2007 or something like that. That was not just about the planet Uranus, or Uranus, depending on how you want to pronounce it.
Yeah, the safe way or the dangerous way.
Yes, that's right. It was lots of questions, in fact, 148, if I remember the number, which came in on radio programs, very like the one we used to do, you and I, in the days when you were broadcasting for the Australian Broadcasting Corporation.
Oh, yes. It's coming up on 3 years since I left there.
That's right. So the book was lots of questions we had from listeners and their answers. And one of them happened to be Why is Uranus Upside Down, which the publishers thought would make a very good title for the book.
Funny that.
And the answer back in 2007 was more or less the same as it is now, but with a lot more detail now. In fact, Uranus is not actually upside down. It's only just upside down. Its its axis of rotation which you remember on the Earth, the Earth's axis is tilted over at round about 23.5 degrees to the kind of vertical in its orbit. In the planet Uranus, it's tilted over by more than 90 degrees. It's 98 degrees. So its axis points slightly to the south of the plane in which it orbits, in which it's really on its side, but you could say at a pinch, yes, it's upside down.
So it's... Yeah, okay. I'm just trying to picture it in my head what it's doing. So it's spinning, what, vertically?
So if you think of something like the Earth, the Earth is spinning anti-clockwise as seen from above the North Pole. And now imagine tilting the Earth over so that it's still spinning anti-clockwise, but its axis is pointing below its orbit plane. So it's tilted over by 98 degrees, 8 degrees more than a right angle. And the reason why, so you might say, oh, well, why isn't it tilted over at 82 degrees? But it's not. The reason why it's 98 degrees is because we denote the rotation, the direction of rotation, as being what specifies what is the North Pole. The North Pole of a planet is the one where the rotation is going anti-clockwise. And so Uranus's North Pole is actually pointing south, which is not a good state to be in. So that's the situation. It's very different from the other planets of the solar system. And we've always assumed that it was because the infant Uranus, back in the early history of the solar system, 3 or 4 billion years ago, was hit by something about the size of the Earth, that an impact actually disturbed it to the extent that when it was formed, it was almost certainly rotating upright in its orbit, but that clout that it received from an impacting body tilted it over. What's now happened, and this is work carried out roughly 6 months ago in the University of Durham in northern England. They have a giant astronomical computer there that simulates all kinds of things like the evolution of the universe and things of that sort. But they've turned it loose on the problem of why Uranus is like it is, and simulated what you get from various types of impact. And they think they have found a recipe that actually produces pretty well what we see in Uranus, because it's not just its rotation that's peculiar. Uranus is very, very cold. The top of its cloud belt is colder than any of the other planets. Not as cold as the dwarf planet Pluto, which is much further out, but it is still very cold. I think it's something like minus 216 degrees Celsius, whereas you'd expect it to be a little bit warmer than that.
I wish it was minus 216 degrees right now, to be honest.
I bet you do, yeah. So it's a bit unfair talking about things like, so unfair talking about ice giant planets when you're sitting in a what approximates to an oven, being slowly basted in your own sweat.
Well, I've actually turned the oven on and opened the door to cool the house down.
There's some wonky physics there, I think, but never mind. That doesn't matter. That's all right. You do whatever you think, right? So why is it so cold? And also, its magnetic field is really peculiar as well. It's kind of off-center. Its magnetic field is not centered on the center of the planet, as most other magnetic fields are, including the Earth's. And so what the Durham University astronomers did was build these simulations with their high-power computer. And it turns out that it looks now as though Uranus was hit by something rather bigger than what we thought before, roughly twice the size of the Earth. But it was a glancing blow. It wasn't a kind of full-on in the stomach type hit. It was basically a glancing blow on the outside of Uranus's atmosphere. And the simulations showed that what happens in that case is the impacting planet basically disintegrates. It falls to bits. It's probably made of rock and ice because it's out in the icy region of the solar system. But they suggest that debris from the impacting planet would have formed a shell around the edge of Uranus, the infant Uranus, a shell of icy material. And that acts as a kind of trap to stop internal heat from Uranus actually spreading to the outside. And so what you've got is this outer shell which is very, very cold, colder than you would expect of a planet like Uranus. That was all peer-reviewed and published. It seems to be very much the best simulation we have as to why Uranus is like it is, with this peculiar tilt.
With you, okay. So the planet that, or whatever the object was that hit Uranus, was destroyed. Why did Uranus survive being a gas giant? I mean, it would seem illogical for something soft and squishy like that to survive a rock-solid impact.
Well, maybe the soft and squishiness of it is what allowed it to survive.
Yeah, maybe.
But the main reason is that the mass of the proto-Uranus, if I can put it that way, as distinct from the thing that ran into it, the mass of Uranus itself is much bigger than the object that ran into it. It's very much a dwarf and a giant situation. The impacting planet being the one that came off worst, because it was by far the smaller of the two. So the other thing that this neatly explains is that this impact would have spread a whole lot of icy debris around Uranus, and it's thought that might have been what coalesced to form Uranus's moons. And that the gravitational effect of Uranus, which by then was already on its side, is to steer these moons into a path that goes around Uranus's equator, because the orbit of Uranus's moons is also the orbits are also essentially parallel to the planet's equator, so they're also tilted over at this comical 98-degree angle. That suggests that the moons of Uranus probably formed after the impact. The thing that's really staggering to me about this simulation, Andrew, is that this whole process took place in a matter of maybe 100, perhaps less, but of order 100 hours.
Whoa.
So it's not something that hung around.
I thought you were going to say 100 years, which would have stunned me, but
it would,
100 hours.
Years stunned me as well, but they say it took place in hours, which is quite remarkable. You don't have to look very far on the internet to find the University of Durham simulation. There's a YouTube simulation showing this actually happening. It's worth a look because it gives you an idea of the way planets behave when they collide, just in case we ever have to face the same issue ourselves here on Earth.
Now, as this is a Q&A question, something you said has prompted a question in my mind. As we know, Earth isn't the only planet that has aurorae due to the effects of the sun and those particles hitting the magnetic field. Does Uranus have aurorae, and if so, where do they appear?
Yeah, the good question. The answer is yes. All the gas giant planets, which all have quite intense magnetic fields, they all have aurorae. And the ones on Uranus occur near the poles of the magnet rather than the poles of the planet itself. I have seen images of aurorae on Uranus, and they are a bit odd because they're not where you expect them to be. That you expect them to be at the top and bottom of a planet, but they're sort of halfway around. Yeah. As where the magnetic poles are.
I suspected that would be the answer. Okay.
Yeah, very, very good. Yes.
Thank you, Fred. Well done. And thank you to Zach for asking that insightful question. Why is Uranus upside down? And Zach, all I can say is if yours is, you need to go and see a doctor. And we do welcome your questions, of course. And enjoy your work out in the desert at Moomba. I was right, southern central Australia. This is Space Nuts. I'm Andrew Dunkley with Fred Watson.
Okay, we checked all 4 systems and keying with a go. Space
Nuts.
Now, Fred, from people with upside down bottoms to people who have dark matter problems, which are almost identical, really. We've got a question here from Travis in Oregon. I'm only calling him Travis because if I try to pronounce his surname, I will be talking for a very long time. He says, hello from Bend, Oregon, USA. Interesting name for the place based on the topics we've just been talking about. I love your show. Here's my question. Since dark matter can only be seen gravitationally, and it accounts for more matter than the matter we can see in other galaxies, is part of gravitational lensing using dark matter, or does dark matter not lens? Dun dun dun. Sorry, I was just trying to be dramatic.
Well, it's better than being smutty, if I may say so.
I would never do that.
Oh dear, space smuts, that's what we should be called.
That's a good name. We might have to change it.
So it's a great question from Travis. I think I just have to spend a little bit of time to explain what's going on. So dark matter, this stuff that we believe amounts to or accounts for something like 70% of the mass of the universe, of the matter in the universe. Why do we believe it's there? Because we see galaxies and clusters of galaxies that should tear themselves apart by their own rotation in the case of galaxies and their own internal movement in the case of clusters of galaxies. They should tear themselves apart if the gravity of what you can see is all that there was. And there is clearly something else there that has gravitational influence and holds them together. That's the bottom line with dark matter. We believe it is some species of subatomic particle that has not yet been identified. There are candidates in the theoretical world, but there's nothing yet to support the theory in terms of practical observations. I did see today, just as a quick aside here, Andrew, that there is a new plan from the people who run the Large Hadron Collider, and that is to build an even bigger Large Hadron Collider, which is going to be called I had my page bookmarked for this.
Slightly larger Large Hadron Collider.
I think it's the LCC, which is it's even larger circular collider. I can't remember. I've lost the page that I had it up on. But they're planning something with instead of a 27-kilometer tunnel under the Lake of Geneva, it's going to be a 100-kilometer tunnel.
Good grief.
Geneva. And the reason for that, the reason why people are now keen on something much bigger than that, is that it looks as though our theories as to what dark matter is have kind of run out. The theories are there, but they've run out of headspace in the practical experiments that we can do. So the energy of the Large Hadron Collider, which is 14 trillion electron volts, is not enough to collide the dark matter particles and reveal them. They're much more massive than that. And so, because mass and energy are the same thing in this subatomic world. So the plans are to build a big new one, which they hope will be ready by 2050, which is kind of pushing it a bit for me, because I'll be 105 then. It's
more than 105 here now.
Yeah, that's right. It's 111. Well, you don't look your age, Andrew, I have to say.
Thank you.
Won't
take long, though, in these conditions.
No, that's right. The collider, if it's built, that will be one of the reasons to try and identify what dark matter is. But just returning to Travis's question, one of the reasons why we are so convinced that dark matter exists is because it actually does gravitationally lens light. And what that means is that anything that's got matter in it actually distorts space. That's the general theory of relativity that Einstein produced in 1915. So a planet or a star or a galaxy or a cluster of galaxies, all of those things distort space. And that distortion acts as a lens on the light of anything that's beyond the object. I mean, the simplest is if you've got a star like the sun, its gravitationally distorted space acts as a lens, and that's actually how Einstein's theory was proved, because the positions of stars behind the sun during an eclipse were seen to have changed. The bottom line is, and to cut to the chase, dark matter does lens light as well. And that's how we can map out the dark matter in a cluster of galaxies, for example, because what you do is you look for much more distant galaxies beyond, and you see them as distorted images, because the lens of the distorted space around the cluster of galaxies actually modifies those images. But you know what they should look like, so you can actually plot where the dark matter is in a cluster of galaxies. It's a very, very powerful tool, and it's actually why astronomers know so much more about dark matter than you might expect that they would. It's because they can map it using gravitational lensing.
Okay, there you go, Travis. You're on the beam. you're spot on anyway, to use an Australian analogy. And well done. Look, I know I joke around a fair bit, but I've been thinking pretty heavily about this sort of question about dark matter and trying to figure out what it is. I have a theory.
The Dunkley theory.
The Dunkley theory on answering the question of what we don't understand in the universe. It's not dark matter. It's doesn't matter.
But dark matter does matter.
Oh, of course it does. Of course it does.
Because without it, we probably wouldn't be here. It's thought to have been the kind of, the nucleus that allowed the hydrogen of galaxies to condense back in the early universe before you and I were born.
I'm starting to realise that just about everything has to be here for us to be here. It's starting to really add up like that.
Yeah.
If there's just one element missing from the entire universe, I'm pretty sure it'd be a very different universe.
The thing is, Andrew, that you're absolutely entitled to comment on dark matter because your name is adapted from the German word for dark, Dunkel.
Is it? Well, actually,
Yes.
I've done the family history thing, and the name is actually English.
Yeah.
It derives from a clearing in a forest named a Lee.
Oh, a Lee, okay.
In the vicinity of Dunk.
But if you were German, you'd be the dark person.
Sorry, Dunker, because Dunker Lee was the original name. We took out the because nobody liked it.
This was in the 14th century.
I don't know when it was.
Yeah.
But it
Anyway.
abbreviated down.
Dark matter is good stuff. We know about it because of lensing.
Yes, indeed. Thank you, Travis. Thanks for the question. We really appreciate it. You're listening to Space Nuts. Andrew Dunkley here with, of course, Fred Watson.
3, 2, 1.
Space Nuts.
To our last question for this episode, Fred, but it's been good to be able to knock off a few questions that have been teasing the minds of the Space Nuts audience. We have one here from Dave and Hedeman, and a few other people have asked similar questions on the same topic, so they may well pick up the answer to their question as well. So we're more or less bumping off 3 or 4 questions at once, I think. Anyway, David says, thanks for doing this podcast. It is easily my favourite science show. I was going to say he must only listen to ours, but he says, I do listen to quite a few different ones. They must be horrible. Anyway, I have a question which relates to an answer Fred gave some time ago. I apologise, but I'm a little behind on in my listening. Yeah, I'm only up to episode 2 of our series myself. The original question related to looking back far enough in time to see the Big Bang, and Fred noted that it was shrouded in Andrew's brilliant fog. I know I've got brilliant fog. Well, something along those lines. However, Fred spoke about it like we were looking at a glow in the distance, but the reality is that we are seeing photons rushing past us as they travel through space. If the period of this glow is finite, and I understand it was about 380,000 years, there must come a time when all the photons will have passed us like ripples spreading on a pond. Very poetic, David, which would allow us to see what is beyond. Clearly, my paradigm is incorrect because the probability of a 380,000-year burst of photons just happening to be passing us now is approximately 3 billion years in the approximate 3 billion year age of the universe seems fairly low. Can you explain the error in my thinking? Yeah, don't write such complicated questions, David, I think would be a start. But Fred, we have come across this question once or twice before, or different varieties of the same question.
Yes, that's right. And in fact, it
keeps coming. Recently. People keep wanting to know the answer to this one.
Yes, that's right. Scott Manser in Sydney, he's asked the same question. So if you're listening, Scott, I hope this helps. And David's question is well put. I understand why he has a problem in understanding what's going on. If we are looking back to a time 380,000 years after the Big Bang, when we see this background radiation, what we call the cosmic microwave background radiation, because it's in the microwave region of the spectrum, all around the sky, why does it only why does it last for apparently much more than 380,000 years? And the answer is we're all kind of looking at it in slightly the wrong way. It's certainly true that those photons of light that have come from that radiation, they're actually photons of microwaves now. They started off as light, but they've been stretched by the expansion of the universe, so they're microwaves. That is true. They are heading towards us, and we are bathed in those photons from every direction, and that's how we know that the microwave background is there. But it's a little bit more subtle than just saying, well, those photons can only be emitted for 380,000 years, and then you see the Big Bang itself. First of all, the main thing to understand is that the universe is very, very, very large. And
here we go. It's hitchhikers again.
The universe is
big.
You might think it's a long way down to the chemists, but yeah, all of the above. It may even be infinite. That's the bottom line. And that gives you a slightly different take on it. And I think the best way to look at it, and I read this many, many years ago, but I think it's an excellent analogy of what's going on, is to think of it not in terms of light, but think of it in terms of sound. And if you, and you might collapse it into 2 dimensions as well, rather than thinking in a 3-dimensional space, because it's easier to do it if you're in 2 dimensions. So, okay, Andrew, you and I go to a concert of our respective favourite musicians, whomever they may be. An enormous paddock somewhere near Dubbo, occupying half of western New South Wales. So there's this field of people full of people. This concert's absolutely full of people. So you've got this enormous area. We're stuck in the middle somewhere with thousands of people around us, and about a mile away at the front there is the band, and they're playing, and everybody cheers at the end of every number, and at the end of the concert everybody goes wild. So we are surrounded by cheering hordes of people. But the band suddenly gets enough of the adulation and signals everyone to stop. And because they do that by waving their arms, everybody stops instantaneously, because the speed of light, to all intents and purposes, is infinite when you're talking about something the size of a paddock. Okay, so everybody stops cheering instantaneously, but you and I are in the middle of this crowd. So the question is, do we hear silence immediately? And the answer is we don't. Because what we hear is after 1 second after the cheering stops, we can still hear sound coming from people 330 meters away, because that's how far sound travels in 1 second. 2 seconds after it stopped, we hear sound coming from people 660 meters away. 3 seconds, we hear sound coming from people 1 kilometer away. But the fact is that the sound does not stop. Those sound waves keep on coming towards us, even though we have stopped and all the people around us have stopped cheering, but we still hear cheering. And if you had an infinite field and you could hear, things for over an infinite distance, then it would never stop. You would hear this. Basically, you've got an expanding circle of silence, if I can put it that way.
Yeah.
With the cheering coming from the outer edge of that. But that cheering circle, if you can put it that way, is receding from us at the speed of sound. So it's getting bigger all the time at the speed of sound relative to us stuck in the middle. If your paddock is infinite, it doesn't matter. That means it will just keep on going. It won't stop. And effectively, that's the situation in the universe. We were, if you imagine you and I standing on a planet that didn't exist when the Big Bang, 380,000 years after the Big Bang had occurred, the universe at that point was still highly luminous. There was photons of light everywhere, cheering everywhere, if you want to put it that way. And then relatively quickly, didn't happen instantaneously, but it was over a very short time, the universe became transparent. And what that means is that you don't suddenly see nothing in the universe. You see you're at the center of an expanding sphere of brightness. And that brightness actually, as I said, because of the age of the universe now, is turned into microwaves. But that sphere is still expanding. So the cosmic microwave background radiation, this wall of radiation that we see everywhere in the universe, is moving away from us at the speed of light. But because the universe is so big, it'll never get to the end. We will always see it, at least for a time that is large, connected with any kind of time that we could observe. So it kind of puts it into a different context. What you're seeing is really an echo of something that stopped a long time ago, but the signal is still coming from us.
Yeah, it's sort of like tax. It just keeps on coming.
Well, that's all right. When you become extinct, they'll probably stop taxing you, although they might not.
No, because in this state, in this country, you pay a truckload of tax when you kick the bucket.
Well, that's right. I couldn't possibly comment on that.
No, it's probably dangerous for me to do that too. They don't like people to know because you're supposed to be dead. Anyway, but that was a very, in all seriousness again, a very really clever way of trying to demonstrate it so that it puts it into our own way of thinking. Because I think, and I don't mean to use this word, but I think our failure in thinking about this is we know time as we know time on this planet, which is irrelevant to the time of the universe and the activities within. So it becomes a totally different kettle of fish.
Yes, that's right. That's right. You kind of got to shift your viewpoint a little bit.
That's why we have astronomers.
That's maybe so. Maybe so.
All right. Thank you, David, for your question, and also thank you to Scott. One point you mentioned a paddock down the road from my house being, half the state of New South Wales. I'd like to explain something to you, Fred. I live halfway across New South Wales. And if I go to the bottom of my hill, there is a paddock. Now, if I walked west from the beginning of that paddock, I wouldn't hit another town until I was halfway across the state.
Yes, I can imagine that.
So you're actually spot on.
Yeah.
I'm right on the edge of this town, and there isn't another major provincial city for about 8 hours drive west of me.
Which is Broken Hill, I guess.
It is Broken Hill, which is also having a wonderfully cool day.
Oh no, they're doing it tough out there.
We've had some massive dust storms here recently. We had one on New Year's Eve, in fact, that wiped out our fireworks display. We had to cancel it, and we had clouds hundreds of metres high, bright red dust. It was just the most stunning thing to see, but most horrible thing to sit through. But that's life out here at the moment. A little bit better in Sydney. You haven't got the heat we've got, but you're getting close sometimes.
Yeah, it's we've had our ups and downs, mostly up.
Fair enough. All right, Fred, as always, thank you so much, and we will talk to you again very, very soon.
Sounds great, Andrew, and enjoy cooling down when it finally stops being hot.
Yes, indeed. Now, I would also like to say thank you to all the people who send in questions and to encourage more. We try to get to them all. Sometimes we answer them by email or on Facebook, but we do try to get to as many as we can on the podcast itself. It can be a bit daunting sometimes, especially when they come in by the dozens, but we don't ignore them. Well, no, we don't. And we will catch you again soon on the next episode of Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.